Hi, I'm Rich Brueckner with Inside HPC. We're here for the HPC User Forum. We have a series of interview videos in lieu of social distancing. So, Paul Muzio, welcome to the show today.
Great to be here. Thank you for inviting me.
Well, thanks, Paul. You know, you're on the steering committee, of course, for the HPC User Forum. But why don't we start at the beginning? How did you get involved with HPC?
There was no such thing as HPC when I got involved with HPC. I was very fortunate to have a number of great high school teachers at Grover Cleveland High School in New York City. This was back in the spring of 1960 when I was a junior. And one of those faculty members called me into his office and said, Columbia University is having this science honors program. Would you be interested? Of course. So I had to go up to Columbia University on a Saturday morning and participate with a whole bunch of people in taking an exam. And then a while later, I got a letter saying I was accepted. And it was really a great program. It was funded by National Science Foundation. It included lectures by outstanding faculty, including I.I. Rabi, and lunch with faculty in the faculty dining room, which provided an opportunity to learn about faculty squabbles and academic politics. But I started the program in fall of 1960, and I was provided access to an IBM 650 computer. No instructions. Here's the computer, here's the key punch machine, and here's the manuals. And so I had to learn machine language to program this machine, which was really basically just a smart accounting machine. 4,000 words of drum memory. It was a decimal-based computer. You know, the instructions consisted of a 2-digit operation code and a 4-digit data address and a 4-digit address of the next instruction. If you wanted to add two numbers, you needed to numerically specify where the numbers started, where the numbers ended. So this was all very basic and fundamental, more like a fancy programmable adding machine. But you learn the most basic level of how computers really work. Except for a 1-credit course in college, this was the only formal computer science course I ever had. And it has served me well for 60 years. Why? Because it taught me the basics, and it provided me with a foundation for understanding both the limitations and the potential for future developments of computing hardware. Unfortunately, I don't think the basics of hardware and machine instructions are taught anymore, and I think that is a mistake, because there's a huge correlation between computing hardware and the applications that can be mapped to the hardware. Conversely, what algorithms and applications we want to solve should drive the hardware design, but it hasn't for the last, 30 years. After graduate school, I went to work as an operations research analyst, and I had to write software to conduct simulations and do statistical analyses. I mostly used Fortran, but I, on occasion, also learned to write COBOL programs. I used a number of different systems, including IBM 360s, 60s and 370s, UNIVAC 1108s, CDC 6600s. And then over time, I moved into other positions at other companies and into management roles regarding technical computing and managing computing systems, resources, and operations. Not so much fun, more bureaucracy and less hands-on work.
Well, I mean, that's how you got started, but they wanted me to have you summarize your HPC experience. So when did you get into
Okay.
the simulation, the science, and the research?
Well, so after doing the research and the simulations and the statistical analyses, I went to work for Grumman Aerospace Corporation. And there I was in more of a management role. And I managed a number of systems for different projects, both the acquisition, installation, and operation of the systems, and then and in the procurement of systems. And I was an advocate, I guess, in 1982 for Grumman to acquire its first Cray 1 computer. It was a Cray 1M. And I was doing that kind of stuff up until 1990. In 1990, I moved to Minnesota, where I worked for the Minnesota Supercomputing Center and was the infrastructure director for the Army High Performance Computing Research Center. And there we had a number of very interesting machines, including a Thinking Machines CM200, Thinking Machine CM5, and then a Cray T3E, and finally a Cray X1. The T3E and the Cray X1 were very interesting machines. The T3E had global address space programming models incorporated in it in hardware. And we'll get onto that a little bit later in terms of future technologies. And the Cray X1, of course, was a scalar vector machine with global address space programming models. I thought it was a great machine. I had two problems with it. Scalar performance was not good, and it was very expensive. So after that, I was director of high performance computing at the City University of New York. And there acquired and installed a number of systems ranging from traditional Dell clusters to an SGI system with 12 terabytes of memory and a lot of GPUs and other systems that were pretty cutting edge technology for the time. I've been retired now for 3 years and enjoying the beach, but still keeping my fingers in high performance computing.
Well, great. Well, Paul, I mean, certainly you've seen a lot of change in your full career here, but what are the changes that you've seen that really struck you in HPC?
Okay, so in certain respects, nothing has changed over 30 years. And in other respects, lots of things have changed. So I'm going to cover what was and what is currently happening and discuss trajectories. There's been advances in computing made by architectural developments and transistor and chip technology improvements. In the 1960s through 1980s, architectural advances such as pipelining, vector processing resulted in significant performance improvements for scientific computers on specialized computers as compared to more general purpose computers. But these specialized machines were to lose out to microprocessor-based chip-based technology. The improvements in chip technology have been revolutionary and astounding. Somewhere in my files, I have a chip from 1964 from an IBM 360 with about 4 transistors on it. Now we see chips with up to 40 billion MOSFETs. These improvements in chip technology have resulted in 1 million times improvement in systems performance, coupled with a reduction in price per computation by a factor of at least 1 billion. In my opinion, the advances in chip technology overshadowed or derailed for a while developments in computer architecture for two coupled reasons. The high cost of building a microprocessor chip fabrication facility required amortization through the sales of millions of chips, not the limited subset required by the scientific computing community. And the extraordinary performance gains in chip technology obviated the need for specialized architectures. Today, we're seeing a shift back to building processes with specialized architectures. This is a result of a flattening performance improvement in chips, particularly related to the inability to increase processor frequency speeds, and also the creation of open fab facilities such as TSMC, which has changed the economic picture. Now, in a way, it's back to the future. We have the proliferation of processor chip connected to a GPU or vector processor. Reminds me of 1985's Digital Equipment Corporation VAX 11780 coupled to a floating point systems array processor. Oh, by the way, that 2020 solution, which is much faster and cheaper, still suffers from the same architectural bottleneck as that 1985 configuration. A poor interconnect compared to processor performance. I expect, however, that we are seeing that problem going away with more advanced microprocessors, which will have integrated scalar vector processors with equal addressability to memory or equal access to memory, like in systems like the Cray one. By the way, along those lines, it was fun a few years back for me to go to classes on programming and optimizing codes for NVIDIA GPUs or Intel PHYs. No different than classes for programming the Cray one or FPS boxes. Made me feel 30 years younger. Also, along those same lines, now we're having, memory and Micron and Intel offering SSD memory. This is no different than extended core memory on CDC 6600s or SSDs on Cray systems. And word addressable, which I think is kind of important. Another architectural feature of yesteryear that I hope to see come back is hardware support for global address space, such as was implemented on the Cray T3E. Writing programs using UPC or Core Fortran was so much easier compared to using MPI, and with better performance on machines that had hardware support for global address space. So I think that's a feature that we'll see more of in the future because I think it's very much important for AI and machine learning.
So, Paul, I'm supposed to ask you about where HPC is headed in the future. Where do you think it's going to go from what you're seeing today?
Well, I think we're going to see more custom chips and chips that are better optimized for machine learning and AI, as well as high performance computing. I will not discuss quantum computers because they're beyond my brain to understand, and my brain is getting old. So. But one of the things with I was at a presentation a while back on machine learning, and one of my colleagues commented to me was, well, this is trivial stuff. You have to show 1 million pictures for it to recognize a horse. And a child can pick that up right away. And I said, that's not really quite true. Child has seen millions and millions and millions of pictures. And one of the difference between, machine learning with a computer and machine learning with biological systems is context. So you don't see a picture of just a horse. You see a picture of a horse in context. You see a picture of a horse relative to a dog, a cat, so forth. And so it's not just understanding the image, it's understanding the concept and the context and the relationships. There's a lot of research these days going on in how does the brain function. John O'Keefe and Britt Moser and Edward Moser won the 2014 Nobel Prize in Physiology and Medicine for the work in discovering the role of place cells in the brain. And place cells are their function is geographic mapping. And so, for example, one of the things they were able to show was taxi cab drivers in London who go through a rigorous training program on maps have much larger developed areas of place cells in the brain. So the brain adapts. It's a muscle, and it grows, and it learns. But the place cells are related to relationships. Getting back to interconnects and global address space models, the issue there is not just machine learning of single things, but linking these things. Artificial intelligence will require linking lots of images and building relationships and graphs between them. And that's where I think the need for improved networks, interconnect networks, and global address space programming models and the hardware to support those models comes into play.
All right, Paul, kind of wrap up here. What are the trends that have you excited these days, and which ones have you concerned?
Well, the ones that have me concerned is exactly machine learning and AI.
Yeah.
1956 a great picture came out in 1956, Forbidden Planet. And the movie was inspired by people in computer science and people in thermonuclear fusion. And it revolves around a planet where the inhabitants had built a machine to run the entire planet, and also where they could transfer their intelligence to it. And their search was for immortality. They would transfer their intelligence to this machine and live on in that machine forever. Well, I often relate that to some of the systems that we're building today. Google has a vast repository of knowledge, and we are transferring ever more information into it. It's getting more capable. I'm shocked over the last 10 years to see how much it's improved, and I expect it will continue to improve. And as hardware architectures advance, it will advance. Are we building that global machine? When we die, our brain is dead, our offspring, they have to go to college and learn all over again. Google doesn't have to. That knowledge stays there. That information stays there. The other thing I'm concerned about is, I've worked with many computer science students, um, and I would go in and ask them, I might have 30 or 40 at a time and ask them, um, you go to Google Maps and you say, I want to go from point A to point B. How long will it take? And Google Maps tells me 2 hours and 17 minutes and gives me the route. And I would ask the students, how does Google Maps know that? Well, my experience has been that maybe 1 in 100 students knew the answer. If some volunteered an answer, they would generally say GPS. Well, it's not GPS. Yeah, GPS shows you the start point and the end point. But the time calculation is done by people's cell phones moving around, even if they're not active, and communicating with cell towers. Where is the level of inquisity among these computer science students to find out what's going on underneath? That concerns me. I would ask them, oh, we look it up in Google. No, figure it out yourself. Let's get back to the taxi cab drivers. Brain is a muscle. The place map cells increased in number because they had to learn maps. We don't have to learn maps anymore. We just look it up in Google. So on one hand, we're transferring knowledge into this artificial machine, and we're losing the capability to think ourselves. That concerns me.
Definitely. Well, Paul, I guess just to wrap up here, what you have anything else you want to add before we close it out?
Well, I just wish everyone stays healthy and happy.
I think that's the best we can hope for. Well, Paul, I hope to see you soon in person, real soon, at the next HPC User Forum, and stay safe. Thanks a lot.
Well, thank you, and you too.
We'll see
Bye
you
now.
later. Bye-bye.